again, it's not that very slow.
All right, so we're very excited to hear Mark to talk about affine determinant programs. And oftentimes I feel like when we're doing program investigation, I feel I'm just learning all sorts of models of computation that I didn't know before. Like we just heard about these reversible circuits by Ran, and now we're here, affine determinant programs.
All right, thank you. Yeah, so the point of this work is just to explore a different possible way to obfuscate programs. So we wrote this about 5 years ago, and at the time, the landscape of obfuscation was a bit different. We didn't have these results showing that you could do I/O from well-founded assumptions. Basically, all we had at the time were tools based on multilinear maps, and we wanted to see if there was something different that you could do that might have might have advantages. A potential advantage might be improved efficiency, so all the obfuscation candidates for general functions are horribly inefficient, so there's potentially a lot of room for improvement there. And then also just by being a different structure, maybe the underlying hardness assumption is going to be different. The hardness assumption is still just going to be the security of the scheme itself, but maybe it's qualitatively different than some of the other constructions out there. Okay, so let's recap the original obfuscation approach, which works something like the following. So first, we're just going to consider NC1 functions. It turns out that this is enough. We can bootstrap these to obfuscate. If we can obfuscate NC1, we can obfuscate everything. And the first step is to use this classic theorem due to Barrington that says you can take any NC1 computation and write it as what's called a branching program. Or for us, we're going to care about this notion called a matrix branching program, which is basically just a bunch of matrices arranged. Most of them are square, arranged in this 2 by n grid. And then you have these vectors that bracket the whole thing. And additionally, each column here is going to be labeled by one of the input bits. And then when you actually want to evaluate it on a particular input, in each column, you read the corresponding input bit. And based on that bit, you select one of the matrices, and then you just multiply the matrices you selected together, and you ask whether you get 0. More or less, this is what you do. And then so that alone is not going to be secure at all. It's going to definitely reveal information about the underlying program. In particular, it's not randomized, and we would expect an obfuscation scheme to need to be randomized. So one thing you can do to kind of add a little bit more security is this thing called Killian re-randomization, where you just multiply all of these matrices by random matrices with the condition that they all end up canceling out. So like between these two columns, I sandwich R4 and R4 inverse, so that when you do any of these multiplications to evaluate the program, they cancel out and you still get the same thing. Now, this alone doesn't necessarily give you security, or doesn't give you security, but it gives you something. Right, it gives you a one-time notion of security, which is where if I give you the evaluation matrices corresponding to one input, so if I just select one matrix from every column according to my input, and I give you that, so I don't give you all of the matrices, just one from each column, that actually information theoretically hides the circuit. All it reveals, it tells you what the product of the matrices are, which tells you the output of the function, but it doesn't tell you anything else. Okay, so the problem is that this is still not good enough. There's still a lot of information revealed in one of these re-randomized branching programs, and there's at least two. There's probably a lot more than two, but at least two things that you might be worried about. So one is something called mix and match attacks, where basically what you can do is like let's say this column and this column read the same input bit. Well, you can do kind of an invalid evaluation where you take matrix 0 from this column and matrix 1 from this column. That doesn't correspond to any input, but you can still do the matrix product, and you'll get something that's either 0 or non-zero, and maybe depending on whether that's 0 or non-zero, it'll tell you something about the way the original function worked. Right, because the correctness guarantee from Barrington's theorem is only that if you do these kind of, if you actually evaluate it correctly, you get the right function. but everything else might actually depend on the circuit itself rather than just the functionality. And there's potentially other things you can do. Here's this one kind of simple thing, which is if you take two matrices from the same column and you divide one by the other, you know, first the two of the matrices cancel, and then you actually get something like this, which is similar to the original, similar in the sense of you know, it has the same eigenvalues as the unrandomized version, and you know, that could reveal more information as well. Okay, so Killian re-randomization is not enough. It gives you this nice one-time guarantee, but it doesn't give you many time guarantees. And so then the next step, and this is just hand wavy, but then you encode all these things in a multilinear map, which more or less, basically what a multilinear map does is it allows you to do the algebraic steps to actually compute the iterated matrix product, but in some sense it doesn't let you do anything else. All right, so you know, there are techniques to kind of force you to do this input consistency, and you can't do matrix division because of the rules of the multilinear map. And we can actually show if your multilinear map is generic or ideal, then actually this works and it's secure. Okay, that's great. But okay, one issue is that doing this encoding in the multilinear map, I mean, it's already not efficient getting to this point, but then encoding in the multilinear map just blows things up even more. And then to make matters worse, I unfortunately didn't put the citations up here, but there were a bunch of attacks, maybe starting 10 years ago, that really significantly damaged the security of these multilinear maps. We did get to a point where we had models of how these multilinear maps worked, where the obfuscation schemes would be secure in those models, but I don't know, it was very delicate, and these attacks really shook our confidence in the security of the multilinear maps. Okay, so that was all background. Now let's get to this work. So the question we asked was, is there something else that we can do in the first steps, right, where we did Barrington's theorem, Killian re-randomization, these kind of really old techniques that were developed for, you know, completely different reasons. Is there something like that? Is there some other method of turning a program into an algebraic structure that allows us to get security directly without then having to throw it in a multilinear map? And if we could do that, you know, one, we might get an efficiency gain, and two, well, if we're not using multilinear maps, then maybe we don't care about all the attacks on them. I mean, obviously now we have to care about the security of whatever structure we're using, but it's going to be a fundamentally different kind of structure, hopefully. Okay. And the thing that we looked at are what we called affine determinant programs. So what is an affine determinant program? Your program is specified by n+1 matrices, where n is the number of input bits. And to evaluate the program is very simple. You just take the linear combination of your matrices corresponding to your input bits. So like you're always going to include A0, and then you include A1 if x1 is 1, otherwise you exclude it, and so forth. So you just take this linear combination of your matrices as a function of your input, compute this matrix, take the determinant, and then you ask whether it's 0. And we'll do the arithmetic over some finite domain just to, you know, make things make sense. And this is a very old structure also. It was used for somewhat unrelated goals. It was used to get like cryptography in very low depth, because the process of converting your function into this affine determinant program is you can do very efficiently. And so what we're going to do is we're going to look and see if we can use programs of this structure to actually do secure obfuscation. All right. And okay, so before that, one like kind of simple view that you can also take is that instead of kind of explicitly thinking about n+1 matrices, you can think of, you actually have a matrix of functions, where each function in your matrix is just an affine function. And how do you evaluate? You evaluate your matrix of affine functions on your input and take the determinant. And that's why we call it an affine determinant program. Okay, so, okay, well, first question is, what can we even hope to compute with affine determinant programs? Are they an interesting class? Do they capture interesting circuits? And the answer is that they do. And basically what we know is that if you have a branching program, then you can turn it into an affine determinant program. So you can actually take your iterated matrix products and throw them into very large matrices, but you can throw them into matrices such that you actually get that the evaluation of the ADP corresponds exactly to the iterated matrix product. So as a corollary, this means we get ADPs for NC1, and that's, not talking about security, but just like we're not talking about security yet, but we know that if we can securely obfuscate NC1, then you can obfuscate everything. So it's enough that we can do this. Yes.
And so what's the dependence on the width of the retrieval? Should I be thinking of it as constant, or does it even work for?
I mean, so Barrington's theorem gives you constant size matrices. This works even if they're non-constant. Yes.
Somewhat related, but how close is the link? Like, if I change a bit, like for instance, read one branching program, does it like translate into something natural on the ADPs, or is it more of a coincidence on one specific?
I don't know if read once gives you any natural restrictions on the ADP. I'm not sure. Okay. Okay. So what can we do with these? So first thing is that we can actually do some analog of the Killian re-randomization that we had previously for branching programs. And basically, it's easiest to see in this kind of view of a matrix of affine functions. So suppose I have a matrix of affine functions A of x. Well, I can just choose random matrices R and S and just multiply on the left and right. And so basically the overall matrix, each entry is just going to be a linear combination of the entries in the original matrix where the coefficients are kind of determined by R and S. And linear combinations of affine functions are affine functions, so B of x is still affine. Okay, so we can do a re-randomization. And just like with Killian, we do get a one-time security notion, which is roughly that if you give me an input x, and I evaluate B of x, but don't take the determinant, I just evaluate B of x, then B of x is actually independent of the original circuit F, except for whatever the output on x is. So, because I can take the determinant, it'll reveal F of x, but otherwise that information theoretically hides everything about the function. So a direct analog of what you get from Killian re-randomization.
You need to multiply on both sides. If you multiply only on one side, it's not random enough.
I don't know. Why not just throw extra randomization in there?
No, it's not random enough. You reveal the kernel of A of x.
Oh, yes, good. Yeah, if you omit one of these, whichever side, the kernel of A of x is revealed.
Also, it's crucial. It exactly reveals the rank, this specific randomization. So it's crucial that if the determinant is 0, then the rank is exactly 1 less than full.
Sure.
So
Yes.
that's the property of this
Good.
representation.
Okay, so what's the good news? So one thing is that this seems to prevent mix and match attacks, just because there's, you're literally just taking this linear combination of these matrices. You're not reading the same input bit multiple times the way you do in branching programs. So at least one of the concerns with using Barrington is alleviated here. But this is definitely still not secure. Even with re-randomizing on both sides. For example, just like this attack where you take the two matrices in the columns and you divide them, you can do the same thing here. You can divide the matrix evaluations for two inputs, and it'll have the same eigenvalues as the original division. And I guess a priori, it's not clear that we can, whether or not these eigenvalues are going to reveal information about the original program. They may. So, this is probably, it's a starting point, it's something. At least it seems maybe a little better in some sense than Killian and Barrington, but we definitely need to work harder. Okay, so here was one thing that we tried, which is an attempt to do some sort of, kind of inspired by what goes on in lattice-based crypto, is to add some error term, right? So now what we do before left and right randomizing by RNS is, so I'm gonna assume that my matrix A has the property that the determinant is always in 0 or 1. We'll see why this is important. So the way I defined ADPs, right, the determinant could be really anything in the non-zero case, but we actually know how to construct ADPs of this form. This is what you get out of the old theorems. I'm also, for reasons that'll hopefully become clear soon, I'm gonna choose the determinants of RNS to be equal to 1. So not just truly random matrices, but having the determinant 1. And why this? I mean, for starters, having the determinants be 1 means that randomizing by RNS preserves the fact that the determinant is in 0, the overall determinant is in 0, 1. Okay, and then one more thing that might be a little less obvious is, so basically what's going to happen is when you evaluate, this error is going to totally mess up your determinant. If your original matrix A had a determinant 0, adding this error might totally mess it up. But the error is always going to be even. And what this means is, like, let's say our modulus that we're working over, let's say it's odd. If your determinant computation actually wrapped around the modulus, adding this even error is going to just basically give you garbage at the end. However, by making sure that the modulus is large relative to, say, the entries of A and E, you can guarantee that the determinant computation here does not wrap around, in which case the determinant of this, the parity of the determinant, is always going to be the parity of the original A.
How do you choose the error?
Let's just say random. I think in the paper we said like just Gaussian entries. Yeah, I mean certainly it can't be as big as the modulus because then you get the wraparound. It has to be much, much smaller than the modulus. Yeah. So anyway, then well, at least we get a correct program. You compute the determinant, parity, and that actually tells you f(x). Yes.
Okay, so this seems a little bit analogous to the BGD FHD schemes where you multiply the error by 2, but you can also equivalently scale the message A by Q over 2 and then let E to be a small error. So is this something similar also here, or when you compute the determinant?
I'm worried that I haven't thought about that, but I'm worried that the determinant, if these entries are big, then the determinant's going to wrap around.
Okay, but it's not something that has been considered, whether that even.
I don't think so. There wasn't much follow work after a paper, and I don't think we consider that on ours.
So everything is really small constants. I mean, all the entries in A, E, B, R are like small constants, or like the.
I mean, they could be exponential, but the point is the modulus. They have to be very small relative to the modulus.
So all the R, S, A, E, everything is small.
R and S can be big.
RS.
Right, because basically, once you take the determinant, because the determinants of R and S are 1, that they go away. You do need them to be 1, though, or I guess maybe they could be plus minus 1 or something, because you don't want it to mess up your parity. But yeah, R and S themselves can be big, and that's kind of crucial. If R and S weren't big, then I'm not sure that adding the error really would accomplish much. Any other questions?
Sorry, the entries of A are small, or just the?
Well, they have to be small relative to the modulus, right? Because I'm taking this determinant.
Yeah.
So if my matrix is L by L, my determinant is going to be like whatever the size of the entries in this are raised to the L.
Yeah.
And so I need the modulus to be even bigger than that. But there's no reason I couldn't take the entries of A to be very large. I think if you go through you know, you go through Barrington's to get a branching program, and then you go through the Shai-Kushulevitz transformation. I think you get basically 0, 1 entries in A, but there's no reason that you couldn't imagine an A with bigger entries. Any other questions? All right. So this turns out not to work either, at least for like I/O kind of security. Why is that? So right in I/O, you actually as the attacker, you know the two. You know, there's two programs being obfuscated. You actually know the two programs being obfuscated, and your goal is just to distinguish which one. And so what that means in particular is for something like I/O, you actually have a guess for what A of X is, right? Because this is just a deterministic, like the A of X function is just a deterministic transformation, at least so far. It's just a deterministic transformation of your function. You know what the function is. So we know what A of X is. And it turns out if you know what A of X is, you can actually recover E of X from this construction. And if you can recover E of X, then you're toast, right? What's the idea? The idea is to look at the determinant of this randomized function, mod 4. Right, so we know mod 2, it's just telling you the evaluation of the function. But we're going to look at it mod 4. And the point is that when you're working mod 4, you're actually going to eliminate anything that's more than linear in E. Right, because you know, if you expand this out in terms of E of X, anything that's quadratic in E will have a 4 in front, and it just gets eliminated mod 4. And so what that means is if you can evaluate this determinant on many inputs, compute the value mod 4, and what you actually get is a bunch of linear equations in E of X. And actually, because the E has a 2 in it and you're looking mod 4, the equations are actually mod 2. So you get a bunch of linear equations mod 2 in the entries of E of X, and you can just solve that using linear algebra. Because you get exponentially many, as many valuations of this as you want. At least heuristically, we would expect this to be solvable, and it tells you E. And once you know E, you can just strip it off, and you're not secure anymore. Okay, in the paper, I'm not going to go into it in the talk, but in the paper, we also discuss actually doing, it's more combinatorial, like basically making the transformation from the original function f into the matrix A, making that itself a randomized process, which seems necessary because at least with this blueprint so far, because you need to hide A of X. A of X can't be guessed by the adversary. So we actually randomize the process of computing A of X. I don't know how much security this really adds, at least defeats that attack. But there was a one follow-up work that attacked some version of our scheme also. So I don't know, I'm not super confident that it does anything meaningful. At least I don't know how to reason about why it blocks attacks. But that's one thing you could try to do to make this more secure, is actually look at the original transformation from function to matrix A as well. All right. Okay, so far this was kind of based off of taking existing constructions of ADPs and trying to randomize them in a way to add security. And we had, I don't know if we succeeded or not, but clearly there were downsides to that approach. So another thing we try to do is to actually just give a direct construction, just kind of like from first principles, just directly see if we can obfuscate a program. And it turns out that we actually came up with a very simple way to do this. Okay, so the first step is we're just going to assume all the NOT gates are in the input wires. That's fine. So now what we're going to do is it's going to be a recursive construction. So we're going to start by obfuscating the input wires, creating ADPs for each of the inputs, and then we'll say, okay, well, if I have two ADPs and I want to take the OR of them, how do I do that? If I have two ADPs and I want to take the AND, how do I do that? And we'll build up this recursive construction. Okay, so I need to show how to obfuscate an input wire and also its negation. Okay, so if my input wire is just xi, well, here's a simple, it's just a one-dimensional ADP that computes the right thing. So in dimension 1, the determinant is just the function itself, and I just, this is a linear function that is 0 on, when xi is 1, and non-zero everywhere else. So, that's a correct ADP, and for negation, you just do the obvious thing too. Okay. Okay. So the more interesting part is how do you combine ADPs? How do you take the or and of ADPs? Let's start with and. Okay. So suppose I have my function f, and it's the and of g and h, and let's say that I have already obfuscated g and h. So I have an ADP a and an I have an ADP a sub a g and an ADP a h. Well, here's a very simple way to obfuscate them. I just write them as a block diagonal matrix. This is still a matrix of affine functions. It's not quite enough. But the key observation here is that, okay, so I'm taking an and. So I need basically what I need is if both of these have determinant 0, then the overall thing has determinant 0, and vice versa, right? Okay, so both of these have determinant 0. That means this thing's rank deficient by 2. And so the overall, this square matrix has determinant 0. So that direction I'm happy. The other direction, though, I'm not happy, right? So in the other direction, actually, if either one of these are determinant 0, then the overall matrix has determinant 0, and I get an incorrect evaluation. So basically, this matrix actually looks more like an or than an and. But what I do is I just kind of randomly shrink the dimension by 1. Right, so I multiply by these big matrices. They're not square. They're, I chopped off, one column here and one row here. And the point is that, so if the overall, overall, let's say I have an and, or I have an accepting input. So this guy's determinant 0, this guy's determinant 0. It's overall rank deficient by 2. And then these random transformations shrink the dimension of the matrix by 1, but otherwise preserve the rank. And so I'm actually down to rank deficient by 1. On the other hand, if one of these was full rank and the other one is rank deficient by 1, well, then when I shrink by 1 dimension, I still preserve my rank, but now I'm actually full rank because my overall dimension was 1 less. All right. So this it's at least correct with high probability. I guess there's some correctness error, like if your R and S don't actually scramble between these correctly or something. But with overwhelming probability, this actually gives you the correct evaluation. The determinant will be 0 if and only if both of these have determinant 0. And I guess I should mention that for this to work, I assumed that not only are the determinants of these correct, but that in the case of the determinant 0, I'm only rank deficient by 1. If these were rank deficient by more than 1, then this wouldn't work. But that's fine. The input wires satisfy that, and when I do this recursive construction, it preserves that property. So everything works.
What could go wrong?
So let's say in the case where g of x accepts, this guy is just 0 or something like that. Well, then the overall determinant is going to be 0 regardless of what happens here. Whereas we need it to only be 0 when this guy happens to be rank deficient.
No, but you said that you can choose the S and R's in a wrong manner.
Just, for example, what if they're what if they're like identity but missing one row or column? Then I'm not scrambling between these, and I won't get the right thing necessarily. Okay, now what about OR gates? So OR gates is basically the same idea, except we can actually, okay, so for an OR gate, we're not going to do this thing where we shrink the dimension by 1. We're actually just going to have the two matrices and then re-randomize them with, like random full rank RNS. And this does give you functionally an OR matrix. But what's nice about an OR is we can add a little more re-randomization to it. And actually, this is also not only, maybe this gives you a little more security, but it also is crucial for the correctness when we move to higher levels. And okay, so what's the correctness issue? So imagine that I'm actually evaluating an or I'm evaluating this or, but imagine I have an input where g of x and h of x are both 1, right? If I didn't have this, if this was a 0 here, well, this guy's going to be rank deficient, this one's going to be rank deficient, so the overall matrix is rank deficient by 2, and then that will mess up the correctness for the AND gates. So what do is we just throw in on the upper diagonal, or upper off diagonal, we just throw in a random ADP here, just totally random ADP. And now what this preserves is that if, let's say, both of these were rank deficient, well, this kind of saves you and makes sure that it kind of cancels out one of the rank deficiencies, and it's not hard to show that, with high probability that that this will actually be correct. That if you have an x that accepts for both of these, the overall matrix will still be rank deficient by just 1 rather than 2. Okay, but you can't re-randomize down here, otherwise you just, your thing will always be full rank. So it's important that this stays at 0 down here. Any questions? Okay, so just to kind of get an idea for the security of this thing, which turns out is not likely to be secure in general, I just wanted to run through some special cases. So for example, if you have a point function, a point function is basically just a big AND, right? And if you take the AND of a bunch of bits, you get a structure that looks like this, right? And the reason, so remember that an AND kept reducing the dimension by, it doubled the dimension, but then reduced it by 1. Well, if you just start with everything being dimension 1, doubling the dimension, reducing by 1 means you're always 1. So basically, for point functions, this thing's just going to give you this is what the evaluation looks like, but then everything just collapses, and you're basically just going to get a scalar, like your ADP is just going to be scalar. Right, so it's going to end up looking like this, where A0 to A1 are just random scalars. And this is actually very, directly what you get is A1 to AN are random, and then A0 is just chosen so that the desired input actually, evaluates to 0. Right? So it actually collapses to something very natural. Now, is this thing remotely secure? Probably not. It depends on what your definition of security is. So for example, if your definition of security is the obfuscation hides the point, then this is actually secure information theoretically, at least for an appropriate size of your underlying ring. And really, it's just because it's just leftover hash lemma, right? You're taking a random vector a1 to an, computing the inner product with your y, and then giving you the output. This is statistically close to random if your ring is small enough. So I'm actually information theoretically hiding y.
Don't you need the rank to be actually quite large though?
The size of the.
Yeah, like for correct.
Yes. So okay, so we get something, right? We get a information theoretically secure point function obfuscation that is somewhat correct. At least we know that it accepts y. But as Daniel just pointed out, when you have a small field, you actually introduce correctness errors, and the reason is like in the range where the leftover hash lemma works, there will actually be many y's that map to the same a0, and all of those y's will be accepted by the program. So
it cannot be information theoretically.
Yes, it cannot be information theoretically secure and have perfect correctness. So whether that's good enough, I don't know, right? It probably depends on exactly how you're using these point functions, whether you care about correctness errors or not. But at least it gives you something. And then yeah, but there, like if you want a better notion of security, okay. So one is you want to insist on correctness. But also, maybe you don't actually care about hiding y in its entirety. Maybe you're concerned even if you leak like a parity of y or something like that. And depending on, you could actually like, if your modulus is even, this thing will actually reveal a random parity of y. And maybe you consider that dangerous. I don't know. It depends on how you're using it. But the point is just hiding y in its entirety isn't necessarily what you want out of security. You might want something stronger, like you can't learn any parity of y, and this would not satisfy that.
Sorry, it would if it was a field, right?
Yeah, if it was a field, yeah, even modulus. Yeah, if it was a ring with even. Yeah, and I don't know. There might be. I mean, I guess in general, you're revealing a random linear combination. I don't know. Is that a problem? I have no idea, but it might be something you're concerned about. Okay, and then over a large field, at least if it's large enough, this is actually insecure. Why? Well, over a very large field, there's going to be a unique short vector that's orthogonal to this matrix. And I guess I didn't write out the rest. But if all of the other vectors orthogonal to this matrix are much, much bigger than 1 comma y, you can just use standard lattice reduction algorithms to find 1 comma y. So at least if you make the field vast, then this is insecure. Maybe there's some middle ground where you actually get perfect correctness, but there's a computational intractability problem there. I don't know. But okay. So there's something here, but maybe it's not the most secure. And then other examples, problems get worse. So let's say I take a single OR gate, right? So I take the OR of 2 input bits, and then I take the AND with the rest, right? So that's going to look something like this, right? So my OR gave me a little blue square here, and now my rather than these RNS being vectors, they're now matrices of width 2. The problem with this is that I'm actually revealing the location of the OR gate, right? Right, because when I did the OR of say 1 and 2, I did this re-randomization, but at this point, like the subprogram that I'm operating on only depends on 2 input bits. So my R only depends on x1 and x2, and that will get revealed when you actually expand out the program. Yeah. So I don't know. Like this method of obfuscating clearly doesn't work for all applications. On the other hand, we do have a positive example where so this is this actually predated this paper on ADPs, and we didn't talk about it in this language, but we actually showed a different. I think it was closely related, but a different method for constructing secure ADPs for the specific case of conjunctions, right? So just an AND of a subset of input bits, and here we were actually able to prove something that is actually secure under LPN. So, I guess this says that at least maybe for restricted classes of programs, you can do something interesting, and well, the hope is that maybe with better re-randomization techniques or other techniques, you could also make it more secure. Okay, so for the last little bit, I wanted to talk about witness encryption. So witness encryption is a special case of obfuscation, or we think of it as a special case of obfuscation. And it turns out that for witness encryption, a lot of these attacks that we're worried about go away. So maybe this actually gives a plausible. Oh, and also witness encryption, just the structure is different, and maybe that could be, maybe we have better luck here. So what is witness encryption? So it's basically public key encryption, but where your public keys are NP statements and your secret keys are the witnesses for those NP statements. So if I give you an NP statement and a bit, I can encrypt to that NP statement, and I can correctly decrypt if I have the corresponding witness. And then the security of witness encryption, so that's correctness. The security is just that if X is actually a false statement, so there are no witnesses, then encryption of 0 and encryption of 1 are computationally indistinguishable. All right, and so this witness encryption is a special case of indistinguishability obfuscation, and it's kind of in the space of evasive obfuscation. So when you're obfuscating evasive functions where it's a priori hard to actually find an accepting input, or you don't know an accepting input, it's like a special class of obfuscation that maybe we have better luck with obfuscating. Okay, so so we gave a candidate witness encryption scheme based on ADPs, and here's how we did this. So first, for witness encryption, it suffices to only consider instances that are part of a particular NP-complete language. You can always use NP reductions to, whatever your witness is, you can always encode it as an NP statement under your favorite NP-complete problem. So we chose the vector subset sum problem, where your instance is a matrix and a target, so a matrix and a target vector T, and I forgot to put the in 0, 1 here. So the statement is whether or not there is a 0, 1 vector such that m dot w equals t, and this is over the integers. Right, so this equality holds over the integers, but what makes this not just plain old linear algebra is that the witness is 0, 1. All right. Okay, so that we know this is NP-complete, and therefore we just need to design an ADP witness encryption scheme for this. So here's one way you might try to do that. So if you're encrypting 0, just output a random ADP. The determinant of this will be non-zero with high probability. So at least we're correct in this case. And then if you want to encrypt 1, here's what you're going to do. You're going to choose random matrices, Ri, and your the ADP that you're going to give out is just a linear combination of these Ri's, where the linear combinations are the coefficients of this vector m dot x minus t. So Ri are just, they're just constants. M dot x minus t is a vector of vector of affine functions in the input. And so if I just take this linear combination here, I will actually get a matrix of affine functions. And moreover, if you give me an input w that satisfies this, when I plug it into A, what's going to happen is this vector will be exactly 0, so the overall sum will be 0 and the determinant is therefore 0. Okay, so at least it's correct. At least this is an ADP that allows you to actually evaluate the witness encryption scheme correct. It's definitely not secure. Why? Well, so far we haven't done anything to actually force the input you evaluated on to be 0, 1. And in particular, right, I can just solve this equation using linear algebra to get some accepting w and plug it into here. The w won't be 0, 1, but this doesn't care. This doesn't care about it being 0, 1. I can evaluate on any vector I want. And if I evaluate it on any w that might not be 0, 1, but as long as it satisfies this equation, the matrix I get is going to be 0. Meanwhile, up here, I don't expect to get a 0 matrix for any input. Right? Up here, I'm just always going to be like when I evaluate the ADP matrix, I'm always just going to get a random matrix. Okay, so that allows me to distinguish 0 and 1 by kind of evaluating on these invalid witnesses that aren't 0, 1. Okay, so we gave a candidate mechanism to kind of add a little additional randomization to get around this issue. And okay, so here's the key observation. So first, I know on an accepting input, this matrix, not only is its determinant 0, it is actually 0. So what I'm going to do then is I'm just going to add to this matrix another matrix B. And this matrix is going to have the property that its determinant is 0 if and only if x is actually in 0, 1 of the n. So the first matrix is kind of what allows me to evaluate the actual instance of the subset sum problem. And this B is going to be what forces me to be in 0, 1 to the n. So if I try to evaluate this whole A on a vector that's not in 0, 1 to the n, this thing here is already going to make my determinant non-zero, and then it kind of doesn't matter what happens over here. Okay, so then it's kind of an interesting question. How do you come up with such Bs? We gave two possible routes. I think
B is going to be fixed.
I mean, B is well, I'm gonna, like, when I encrypt, I'm gonna choose a random B, a random ADP B with this property. But it won't be a fixed B. It won't be a fixed B. Like, every time I encrypt, I choose a different B. Okay, and so now the challenge is, how do I create an ADP that has this property that if I try to evaluate on, that is, it accepts everything. It accepts all the valid inputs, 0, 1 to the n, but rejects everything else. So here's an interesting way to do it. So what I'm going to do is, I'm actually going to, like, explicitly write out what, okay, so we know that on some input x and 0, 1 to the n, that there's some kernel vector, right? So I'm just going to write out the kernel vector as some function. The kernel vector is going to be some function of the input. And I'm just going to, like, write that out as a formal expression. You could choose whatever kind of formal expression of your input you want. Here's a particularly natural one that I'm just saying, well, my kernel vector is just going to be 1, x, where x is whatever the 0, 1 vector is. You could do something different here. Like, you could make this random linear combination of x. You could put degree 2, 3, whatever. Like, you could put anything you want here. Just some like polynomials in x. And now what we're going to guarantee is that this, whatever is here, is always going to be a kernel vector of B, B of x, right? So you can expand this out, right? So B of capital X is B0 plus B1x plus, sorry, B1x1 plus B2x2 and so forth. And so what's the point? So somewhere in here I need to like utilize the fact that x's are in 0, 1. So far if I guarantee this kind of naively, that this is like identically 0 as a polynomial, I'm still not going to prevent these kind of invalid input attacks. But here's what I do, is I notice that when I compute this product here that has to be 0, I'm going to get some terms that are quadratic in my x variables. And the key thing to notice is that, well, if x is in 0, 1, any square I can just erase, right? So x1 squared just becomes x. And this is crucially not true of anything that's not 0 and 1. So, so I expand everything out in terms of these formal variables xi. I do this substitution where I replace every xi squared with xi. And now what I have is I have this formal expression in these x1, x2, whatever variables, and I know it has to be 0 on the left. It has to be identically 0. Which means that, like, all of the coefficients on the right-hand side, if I take the coefficient of x1, x2, that has to be 0, and so forth. And that just gives me a bunch of linear constraints on these B matrices. And so I can just solve that linear system. I can compute actually a random B solution to that linear system. And what is that going to spit out? It's going to spit out exactly an ADP with this property, at least with high probability. You have to play around with the domain sizes, maybe if you wanted to ensure that there just simply don't exist any accepting inputs other than the valid ones. But yeah, intuitively, right? If I give you an x that's not in 0, 1, you would be, like, if I had stopped here, you would be correct. But because of this substitution here, you're just going to get like a random evaluation. Yeah, and we gave another like more explicit method for coming up with this B matrix by kind of carefully directly constructing it, but I think this is the conceptually nicer one. Yes, question?
Is this an if and only if characterization of all B satisfying this equals to 0 if and only if it is 0?
I don't know. So I think I'm kind of making a stipulation. When I saw this, I'm making a stipulation about what the kernel vector is.
Yeah.
Right? So I think this is a characterization of all B matrices that have the kernel vectors be this function of X.
You can take a general branching program that checks whether all inputs are 1 and apply the previous generic transformation. And branching programs are sufficiently expressive so that
Right.
you have it's intractable to figure out what a general branching program that does it looks like.
Yeah. Good.
But these are only samples some distribution of B.
Yeah. Basically, it samples the distribution of B where the kernel vector is this function, but there could be other functions, and in general, you won't be able to tell whether a B you sampled is this all except program or not. Yeah, actually, that's all I really wanted to say, and it looks like I'm good on time. So, are there any other questions?
I'm still a little confused about the different parts of the talk. So, like, this witness encryption is not really connected to the candidate obfuscation, but what's the status of the candidate obfuscation? Like,
I would think I would deem it insecure. So at least the version that we had written up with these additional randomization steps that I didn't go into. I believe that was what was attacked by this one paper. They gave another candidate that re-randomized it better, that blocked their attack. I don't know. It feels a little bit like kind of the days where we were, there was an attack on multilinear maps, so let's add some more randomization. Eventually, we figured out how to get around that.
It could potentially still be secure in the context of natural applications.
Yes. Yeah.
So it's kind of a leakage attack, and the leakage, you could have potentially defenses like the Chenetal paper suggested, or generic defenses like Mark mentioned, alluded to in the multilinear maps, right? So you have this DCC paper that suggests some generic defense.
Yeah.
Or it could be secure as is in the context of natural applications.
Yeah. So for some functions, maybe it's secure. For other things, maybe we have to use new ideas to make it secure. I guess the point of witness encryption is it's not just it's a relaxed structure because we just need to handle whatever NP complete problem, but also it seems like getting accepting inputs is a problem, just like it is in the multilinear map setting. And the Chen et al. Attack also was they crucially relied on the ability to get accepting inputs. If you can't find accepting inputs, then maybe even our candidate is secure, but it definitely needs more study.
Maybe adding a bit more to the witness encryption, again, as far as we know, it has not been broken yet for what it's worth. And second, in the paper, we give some concrete numbers, maybe slightly on the optimistic side, but this is certainly implementable for non-trivial applications.
But do you have the presumed time bounds, lower bound on the time to attack it, or?
For the what? For witness encryption, there are no.
No, I meant for the obfuscation.
For the obfuscation.
You mean concrete bounds?
Just to give some counter example.
So the attack is efficient. It's not, you cannot.
Yeah, it's polynomial time. Specific.
I'm talking within polytime. I'm thinking of can you do anything reasonable that will be secure against a reasonable amount of work, but not slightly above.
That I'm not sure.
The attack could be fixed heuristically. There was even the paper presenting the attack even suggested a fix. So it's kind of like the GGH plus 13 situation.
So for the point obfuscation, could you guarantee, let's say for a password application, if I choose a random Y, is it hard to find a different Y prime where they collide?
That basically turns into it's basically like solving cis, right? A 1D cis instance. So in some cases, so you're saying in the small field case where there exist collisions, You're asking whether it's hard to actually find?
Yeah, I guess that'd be one application I would actually hope to be true.
Yeah, I mean, presumably, because it's you're basically in the 1D cis case, right?
Okay.
Right, because literally, yeah. I think that's equivalent to some really, right? Because you just take the difference of your two colliding points, and that's now a vector that's orthogonal to this this random vector.
Okay.
Maybe again relating to Paul's talk about our wiretap work, just trying the ADP obfuscation as a heuristic substitute for ideal obfuscation in this specific context. I don't think we tried. Do you have an answer?
I don't have any idea. Yeah, not sure.
Some more questions? And just a reminder, there'll be a high agenda program today, so if you're interested.